Is it visible to you?
Yes, sir.
Yes, sir.
Okay, thank you. Okay, so let us recall our last class we have discussed. In the last class, we have discussed linear dependence, independence, and we have seen some examples. And then we have defined a row echelon matrix. Linear dependence. Elementary row operations, then row echelon matrix. Okay. So today we will keep this. We take a pause from discussing these two things, row echelon matrices. Okay, we'll learn how to find the row echelon matrices. But before that, we need to discuss some more definitions from after this linear dependence and independence. We need some important definitions. Okay, some three or four important definitions. These are called spanning set. Spanning set of a vector space. The basis of a vector space. A dimension of a vector space or a subspace. Okay. After discussing these things, we will come back again to the because the ideas of these things will be applied row reduced echelon matrices, okay, to study the system of linear equations. From here, we will go to equations. Okay. So let us go to the first definition, that is a generator or spanning vectors. Okay. Now the definition is that if we have v1, v2, and vn in vectors in the vector space of over the real field, over the field of scalar, field of scalars is actually is a real number set. Okay. N vectors are there, and suppose S is a subspace of V. S can be also equal to or the subspace of V. S may be equal to V. Then, if every note that if every element of S can be written as a linear combination of these n vectors, then we say that these vectors will generate the subspace S. Okay. In particular, if when S is equals to V, then we say that this n vectors will generate the vector space V. Now, we denote this event as span of v1, v2, and vn is equal to S. Now, if we want to see some examples, suppose S is our 1, 0 and 0, 1. Then, and V is our vector space, the two-dimensional space, R2. Then we can show that R2 plus dot is a vector space over the field of scalars, the real number. Okay. Now, can I write span of, question is, can I write 1 is equals to question. Whether it is true. Okay. In order to show this, what we have to show? We take an element from the real number, from the two-dimensional vector space. Okay, R2. That means here now, if every element of S can be expressed as a linear combination of these n vectors. Here we are taking only 2 vectors. So let us see. X comma y is equals to x into 1 comma 0 plus y into 0 comma 1. So we can write it as a linear combination of these 2 vectors. So this relation will hold. So that means 1 comma 0 and 0 comma 1 and are generators of R2. That means with these 2 vectors only, the span is the extent of these 2 vectors. Span meaning, okay, if you find out the dictionary meaning of span, that means span of something, that means there is the extent of those particular thing. So here we are talking about span of these 2 vectors. 0, 1. Okay, this is actually the whole space. Now, if you think about that graphically, so graphically, if we think about this thing, okay, so our suppose 1 comma 0 is here and 0 comma 1 is here. Okay, we pick any point here, x comma y. We can find suitable x and y. Okay, depending on x and y, we can find suitable these real numbers, suitable scalars, so that we can write it as a linear combination of these 2 vectors. Okay, if you find it here, so here also. So each and every point in this 2-dimensional space can be written as a linear combination of these 2 vectors. So that means you will cover all the whole space. Okay, the extent of these 2 vectors is actually the whole space. Okay, there may be only 2 vectors, but their span is equal to the whole space. Okay, similarly, now the question is there only, is it the only set that can span this whole space? Okay, actually the answer is no. There may be more than one spanning set.
Sir, can you explain once again graphical verification?
Okay, that graphical, yes. So graphically, if we consider, now think about this. What is a linear combination? Linear combination, if we can write, if we can find, okay, for Victor linear combination. So V is a linear combination of vector C1. If we can write it, V, P1, P1, C2, P2, Pn, Pn. Okay. So what we are telling that if we have a two-dimensional space, okay, we are taking a particular points 1, 0 and 0, 1. Okay. Now, suppose we take here 5, 6. So 5, 6 is belongs to R2. Okay. Then 5, 6 can be written as 5 times 1, 0, the vector V1, and 6, 6 into 0, 1. So here what is C1 is 5, C2 is 6. This is V1, V2. So only two vectors are there that can find. So suppose here it is. Here it is. 5, 6 is somewhere here. So that means you are able to go by this combination. You can get this point by these two particular vectors. Okay.
Sure.
Similarly, for any other point, you can go there also. By suitable choice of scalars. Every point. This way, in this two-dimensional space, you take any point xy, we can write it as a linear combination of these two. So,
Sir,
yes, tell.
sir, in the definition you said any element of subspace can be written as linear combination of a vector space. But in example, you took an element from the vector space x comma y and you represented it by the linear combination of two elements in subspace.
No.
Sir, in definition, you said each element of subspace space can be represented as a linear combination of vectors which belong to vector space. In example, you took an element from the vector space x comma y, and we represented it by the linear combination of two vectors in the subspace.
Okay. Then what is your doubt?
Like, is definition different or?
No.
Because
Different.
in the example we took x comma y from vector space, no sir.
It is not for any two vectors. It is not possible. See
No,
the
sir.
definition.
In
Definition
example,
says if every element of S.
In
Okay,
example, we represented x comma y as a linear combination of this, no sir.
No.
X
it
comma
is not.
y belongs to vector space, no sir.
Which one?
In example,
Y are scalars.
in example, x comma y equals to x into 1 comma 0. We wrote that, no sir.
Yeah, that is true.
On LHS size, x comma y, this coordinate is actually from the vector space, no sir. LHS side.
Okay, this one.
Yeah, this one, sir.
Okay. See,
It is from vector space, no sir.
I told you that this can be S can be equal to V also.
Yes, sir. But there are sometimes S may be not equals to V, no sir. Actually, in example,
S may not be.
V as a linear combination of S, no sir. In example.
Yes, it is. This is a particular example.
Yes, sir. In example, on LHS side we took V, and on RHS side we took constant x comma y and linear combination of subspace we wrote, no sir. But in definition, you said S can be represented as linear combination of any elements of V. But in example, we represented V as a linear combination of S.
No, I think definition is correct. For this particular example, I should have taken some other example. Okay. Okay. I got your doubt. Okay. I understood where you got this doubt. Okay. So this is actually.
And also, sir, I have another doubt about the definition, sir. As S is a subspace of, you said no, sir. As S is a subset of V.
Yes, subspace.
Subspace of V. So any element from S can be an element from V, no, sir.
Any element from S.
All the elements which are present in S is all the elements which are present in S will be surely present in V, no, sir.
Yes, of course.
So then it automatically we can choose any constants in V such that we can represent S, no, sir. So it's true for all conditions, no, sir. If we come from this side.
Yes, it is true. It is true.
So then, like it is true for every subset and set. If we take, no, sir, then why we need to define spanning? Because if every element which is present in S is also present in V, so if we take any constant like 1, 0, 0 or 0, 0, 1, anything we can take, we can represent the elements in S, no, sir.
Yes, we can do that.
Sir, I think it is V, sir, instead of S. If every element of V can be, I don't know, means according to the example you said that you said to us.
No, just a minute.
Sir, it works only for 2 dimensions.
No, it will work for every dimension.
Okay.
It will work for, let me give you one example. Okay. We take an example from R3. S is a subset of R3. Okay. So then we take vectors V1, V2. This is our V1.
Yes, sir. In this you represented S, sir, but in the before example you took X comma Y belongs to vector space. In example, before example.
Okay. Okay. Now is your doubt clear now?
According to definition, this example clarified my doubt, sir. But in before example, you took X comma Y from a vector space, sir. In before example.
Here.
Already you defined S as 1, 0 and 0, 1 and
no,
you took
here S is equals to R2 actually, V. S is equals to V actually. We are taking.
In this example, sir?
Yes, in this particular example, we are taking S equals to V. So the definition is completely correct.
Example.
See, S is in the next example, what we see, this S, this particular subspace is a span of these two vectors. But these vectors also belong to the vector space V.
Yes, sir.
Okay.
Yes, sir.
Sir, once again repeat the definition, sir. The confusion.
Okay. The definition says that, okay. We consider, suppose the definition is actually this one. If every element of S can be expressed as a linear combination of V1, V2 and Vn, then we say that V1, V2 and Vn will span the subspace. That is the definition. Okay. So if you think about the three-dimensional space, okay. if we think about the three-dimensional space, V is our three-dimensional space. Then, in order to span this in this whole space, we need to think about three vectors. Okay, a subspace can be generated by these two vectors, but we need to include three vectors. Without these three vectors, we cannot span this whole space. Okay, for any vector x, y, z belongs to R, okay, belongs to you can call it V. Here it is V. Then x, y, and z can be written as x 1 0 0 plus y into 0 1 0 z into 0 1 0 0 1. Okay, so the span of these three vectors is actually R3. Similarly, you can define now hereafter we will call it unit vectors. Okay, these are unit vectors, identity vectors. We call it E1, E2, and E3. Since they are a standard form, they are actually standard vectors. So we will call it a standard unit vectors actually. Just like we have seen in two-dimensional case, I equals to 1, 0 and j equals to 0, 1. Okay, so unit vectors. In Rn, in n-dimensional space, E1 is actually 1, 0. Okay, n components. Then E2 0, 1, 0, and so on. And En will be 1, 0, sorry, 0. Okay. So the span of Rn, span of E1, E2, En. Okay, it will be the whole space Rn. Okay, for R for n equals to 1, 2. Okay. Now there is a basis. There is a definition called basis. What is a basis? Suppose V be a vector space over the field R. Then a set of vectors, okay, will be called, is said to be a basis if it satisfies two conditions. Okay, this must be a linearly independent set and they must generate the V. That means any element of V, x belongs to V, can be generated by this n vectors, can be written as a linear combination of these n vectors, and provided this V1, V2, and Vn are linearly independent. So one trivial example is that if you consider V equals to R3, then and B equals to V1, V2, and V3, where V1 is 1, 0, 0, V2 is 0, 1, 0, and V3 is 0, 0, 1. Okay. So, as we have already seen, these are linearly independent. And also we can prove that for any x1, x2 and x3 belongs to R3. Okay, so linearly independent, first condition is satisfied. The second condition, it is x1 x2 and x3 can be written as one zero zero plus x2 into 0 1 0 plus x3 into 0 0 1. So this implies that span of V1, V2 and V3 is equals to, okay, since these two conditions satisfies, so we can call it, this is a basis for R3. Okay, now the question is it the only basis? Can there be more than one basis? Okay, the answer is yes. We'll see another example. So here V1 is given as V1, V2 and V3, and V1 is 1 1 0 1 1 1 and V2 is 1 1 0. Similarly, V3 is 1 0 0. So in order to check whether it is a linear combination or not, what we have to do, linearly independent or no, it is sufficient to check whether the determinant is non-zero or not. So we calculate the determinant. So this is -1, non-zero. So it implies this V1, V2 and V3 are linearly independent. Okay, now can we write any x1, x2 and x3? We have to check whether it is a spanning set or not, belongs to R3. Okay, so if we can write x1, x2 and x3 as it is 1 okay 1 1 and 1 plus some suitable constant 1 1 0 plus 1 0 0. Okay, then what if we can find some suitable constants C1, C2 and C3, then we can say that this can be represented as the linear combination of these three vectors. Then it will show that the span of these three vectors is actually the whole space. Okay, so if we select here x3, then let me write down clearly. Then it is x2 minus x3 and x1 minus x2. So that, okay, since this is a symbolic for any given particular 5, 6, 7. Let us check whether it is a linear combination or not. Okay. So what we do? 5, 1. No, this will be 7. X3 is 7. 1, 1. Plus x2 minus x3. So that means x2 minus x3 is 6 minus 7 is 1. Okay, 1, 1, 0. Plus x1 minus x2 minus 2. Minus 1. So minus x2. It is 0, 0. If we go here, let us check whether it is true or not. Seven minus one, that is 5. 7 minus 1, 6. So 7 minus 0, 0. Okay, 7. Okay. So if we can select, we can select this particular constants, particular scalars. Okay, not constant. We will call it scalars. Okay. So this particular vector can be written as the linear combination of these three vectors. Okay. In order to, if we consider arbitrary x1, x2, and x3, and if we can select this, if we can find particular scalars c1 as x3, c2 as x2 minus x3, and c3 as x1 minus x2, then we see that v1, v2, and v3 are the generators of R3. So that means we can write span of v1, v2, and v3 is actually the whole space. So this is also, since already we have seen it is linearly independent, so we can say that the set B1, this is given B1, the given set B1 is also a basis of R3. Okay. Now the question may come that whether a vector space has only two bases. Okay. The answer is no. Okay. A vector space may have infinitely many bases. If the set is infinite actually, so R2 is actually infinite set, R3, R2, R3, Rn is an infinite set, so may have basis. Okay, more than one basis, we have seen here that at least two bases are there, but there is a theorem that it may have arbitrary number, infinite number of bases. Okay.
Sir, can you repeat again that the two bases?
Which one?
Two bases, sir.
Second basis.
How to make sure?
Okay, for any given set, you have to check whether it is a basis or not. Okay, is that clear? That we have seen actually that B1 is a basis. In order to show, given any set of vectors, we have to check whether it is linearly independent or not. Okay, we have seen that we can by shortcut method that if we check, if we can check that the determinant of these vectors. Okay, we will write these vectors in the row of the matrix, and we take the determinant. If it is non-zero, then we conclude that they are linearly independent. Okay, in order to be a basis, okay, will it must satisfy two conditions, that it should be linearly independent, and second condition is it should be the spanning set. Okay, these two conditions has to satisfy. So first condition we have satisfied. Now we have to check whether it is a spanning set or not. For a spanning, whether it is a spanning or not, we have to take one arbitrary element from the vector space V, and we can check if we can write it as a linear combination of these three vectors. Okay, these three vectors, then we will conclude that this is a spanning set. So once these two criteria are satisfied, then we can call it a basis of the given vector space. So that is the idea. So earlier we have seen this is our standard basis. Okay, 1 0 0 1 0 0 0 1 0 and 0 0 1. This is hereafter we will call it a standard basis. Standard basis. Okay. So we can see a vector space V has more than one vector, more than one basis. It has one basis, more than one basis. So here we are seeing B1 is also a basis of R3. Okay. The question is, so we can see that now the question is whether it has only two bases. Yeah, the answer is no. It may have two bases. Some vector space may have two bases, but in general, vector space may have more than one basis. That's it. Okay. For your purpose, you can forget about this infinite number of bases, because we will not go into the details of it. So you may escape this. It is sufficient to know that a vector space may have more than one basis. Okay. Is that clear, Appu?
Sir,
Yes,
Sir?
sir.
can we choose scalars as a wish, or we should belong
No.
to vector
It
space
has
only?
to be a linear combination. Like in the last class we have seen, right?
Yes, sir.
If suppose two linear combination, we have seen that not every vector can be written as linear combination of some particular vectors. You may have
Yes,
some
sir.
V. Okay, you may have some V1, which may not be a linear combination of these three vectors. Okay. But since in this particular, since it forms a basis, okay. So any vector from R3 will be a linear combination of these three vectors. We may have in a different example, okay, in a different case, we may have some three vectors V1, V2, and V3. We may have, okay. So we will select one vector V from the vector space. Okay. If this V cannot be written as C1 Q1, C2 V2 plus C3 V3, then what we say that this particular set, the given set, okay, is not a basis because it is not able to give us this linear combination. If it is a basis, then we will be able to write this way. Okay, it will span this base. Span every vector can be written as this linear combination of these three vectors. So if we cannot write that means that span of, okay, for this example, span of B is not equals to B, then that means it is not a basis. Okay, suppose this is B2 actually. So in order to distinguish, because we have already defined B and B1. So suppose for some B2, okay, and a vector space B, we may not be able to write this. Then this B2 is not a basis. Okay.
Sir, why we return C2 as x2 minus x3, C3 as x1 minus x2?
Actually, it has, you have to calculate. If you solve, okay, in the last class we have seen, right? Do you remember?
Yes, sir.
Okay,
Yes,
how
sir.
to how to calculate this constants? We write on. Okay, how to calculate this constants? We will write that for any given particular x1, x2, and x3 as a linear combination of C1, 1, 1, 1 plus C2, okay, 1, 1, 0, and then C3, 0, 0, 1. That was, sorry, that was the vector that we can see 0 and 0. So from here you will get a system of linear equations. Okay.
Okay, sir.
If you solve this system of linear equations, then you will get C1 as x3, C2 as x2 minus x3, and x2 minus x1. Yes, tell.
Okay. Okay, sir.
Okay. In the last class we have seen, right?
Yes, sir.
Okay. So let us move forward. Okay. So this is a particular, a very special example of vector space. Okay. We are considering a vector space actually M 2 by 2 matrices, collection of all 2 by 2 matrices. Okay. Then we can show that this vector space V, here V is our, now the vectors are like matrices, 2 by 2 matrices. Okay, this addition is actually matrix addition, and this multiplication is matrix multiplication. So this will form a basis. Sorry, this is a vector space. We can conclude that this is a vector space. Okay. Here, if we take the standard basis, okay, for this matrix space actually, matrix vector space. For this vector space, as you can see that if we select B is actually 1, 0, 0, 1, 1, 0, 0, then 0, 1, 0, 0, then 0, 0, 1, 0, and 0, 0, 0, 1. So if we consider this 4 matrix, okay, here we call it a V1, V2, this vector, V3, and V4. Okay. Then we can prove it. It is easy task to check. This is a linearly independent set. Then the task is to select any x1, x2, x3, and x4 belongs to the set, belongs to V. That V is our here M2 by 2. Then we can write x1, x2, x3, and x4 as x1 is the linear combination of, okay, these 4 vectors 1, 0, 0, 1. plus x2 as 0, 1, 0, 0 plus x3 as 0, 0, 1, 0, x4 as x4 into 0, 0, 0, 1. Okay, since it is spans the, so from here we can write a span of this B is actually M2 by 2. So these two conditions are satisfied. These two criteria, okay, one is linearly independent and another is spanning the whole space. So these two criteria are satisfied. So this is a basis of M2 by 2. Okay. So this is also for this particular vector space. This is a standard basis. Okay. Now the question is whether this B, the given set of vectors, is a basis or not. Can you check and quickly tell me? I'm giving you 2 minutes. Not 2, 3 or 5 minutes, because you have to calculate the C1, C2 and C3 also.
So can you just go back to the previous question for a minute?
This one?
Yes, sir. Thank you, sir.
Okay. I will share the PDF first. No need to write and copy. Anyway, you can take if you want. Okay, because if you want to engage, so it is better to write also. So the answer is actually, it will be a yes actually. It is a basis. Okay. It is a task actually. So this is home task since you are in home. So this is called, I'll call it a home task.
So can you just do the spanning part?
Spanning part, you have to calculate. You have checked it, right? Independent.
Independent I check, sir, but the spanning part I'm not getting.
Okay. So for a spanning part, you have to say x1, x2, and x3. You have to check C1 into 1, 0, 1, 1, 0. C2 into 1, 0, 1 plus C3 into 0, 1, 1. Okay. This is C1, C1, 0 plus C2, 0, C2, 0, C3, and C3. Here C1 plus C2. Then you are getting C1 plus C2 here, C3 plus C3. Finally, 0 plus C2 plus C3. C2 plus C3. Okay. So we have a system of linear equations. We have to find C1 plus C2 is actually X1. C1 plus C3 is actually X2. And from here, X2 and X3. And C2 plus C3 is actually X3. Okay. So if you solve these three equations, what you are getting?
Sir, C1 is equals to x1 plus x2 minus x3 upon 2
X1 plus X2
minus x3 upon 2.
Okay, minus X3 divided by 2. Then
Similarly,
C2,
C2 x1 plus x3 minus x2
X1 plus X3 minus X2
upon 2.
upon 2. And C3,
Then x3 plus x2 minus x1 upon 2
X3
plus
plus
x2
X2
x minus x1
X1 upon 2.
upon 2.
Okay. Okay, so that would be our those constants, the scalars. Okay. C1, C2, C3. So this is also a basis for R3. Okay. Okay. Now just let me quickly tell what is the meaning of a dimension. Okay. I'll come back to this problem again. So dimension of a vector space. Dimension of a vector space is actually the cardinality of the basis. Okay, now the cardinality is how many elements are there in the basis is actually called dimension. Okay. Okay, the number of vectors present in the basis, okay, of a vector space V is called the dimension of V. Okay, since if you remember that basis, standard basis for R2 is actually so the dimension of this is a basis for R2. So the dimension of, we'll write it as, it is denoted by dimension of V. V is our here, 2, R2 is actually 2. Now since our school level, we have been saying that this R2 is a two-dimensional space. That is the meaning of it, that this space is actually generated by two linearly independent vectors. Since 1, 0 and 0, 1 are easy to visualize, easy to understand, so we'll use on, we have been using the standard basis. In most cases, we have used standard basis. But today we have seen that a vector space can have more than one basis. So in four-dimensional space, R4 has dimension 4. Okay, that means R4 is a span of E1, E2, E3. This is a standard basis E4, where E1 is actually 1, 0, 0, 0, and E2 is 0, 1, 0, 0. E3 is 0, 0, 1, 0, and E4 is 0, 0, 0, 1. Okay. Now, when we consider n, so that the size of the vector becomes n tuple. Okay, n. The dimension is also n. The basis is actually n. Is actually 1, 0, 0, 0, 1. 0. In this way, we will understand. Okay. So that is our dimension of a vector space. Sometimes this dimension is actually called a rank of a vector space. Rank of V, okay, is the dimension of V. Okay. So I will stop here. Okay. And few things are there that I will discuss in the next class. So one more thing I want to tell you that every class note will be uploaded to the LMS server. Okay. So I have seen many of you have, I mean most of you have already logged in to your